Welcome back to my channel. So in this video I want to explain the problem with the, I can't pronounce that, I'll call that the HK experiment. Okay, so if you don't already know, I've made a video called The Real Solution to the Twins Paradox and Why Einstein Was Wrong. And if you didn't watch that video, you kinda have to watch that video before you watch this one. Okay, so watch that video and come back. So, now that we have said that light cannot be constant for all frames of reference from the previous video, that means that Einstein's time dilation is wrong. But what about this experiment and some others that have been done to prove special relativity and time dilation? So I'll be looking at this experiment. I'll be telling you not the problem, but the reason why this experiment doesn't prove Einstein's special relativity. Okay. Okay. So what is the HK experiment? So after reading on it, it's basically an experiment where two scientists have traveled with an airplane around the world, came back to the same place, and they took an atomic clock with them, and then left another atomic clock on Earth, not traveling, and then they saw if there's any difference in the time in the atomic clocks, and there actually was. And they said that this proves special relativity. Okay, and something to note is that atomic clocks are very accurate, and they shouldn't vary in time if for no reason. Okay, so now I probably need to know how do atomic clocks work for me to explain anything. So, how do atomic clocks work? According to this website, they work by first of all having a device that can produce frequency of light, and then measuring that frequency of light, and measuring the amount of cycles of that frequency of light, and yeah, they produce a frequency of light where they know the exact amount of cycles that pass a specific point in 1 second, and then they measure this frequency, and they measure the amount of cycles that pass, and whenever that specific amount of cycles pass, they say that 1 second passed, and so on, and they count the second. And how they adjust the frequency is how they adjust the frequency of the light they use is by using atoms and using something called resonance of atoms, or yeah, so basically they adjust the frequency by having a specific atom and providing it with different frequencies of light, and they adjust the frequency so that for a specific frequency they know that a specific atom can change the energy state of its electrons, so they use this atom to adjust the light to a specific frequency that they know. So basically that's what they do, and then when they know this specific frequency, now they can use this frequency to calculate 1 second, because they can use the amount of cycles that pass. Calculate the amount of cycles that pass in 1 second, and when they measure this amount of cycles passing, they measure the 1 second pass. Okay. Okay. So now that we know what's the HK experiment and how the atomic clocks work, what is the problem with the HK experiment? So, the problem with the HK experiment is that even though the atomic clocks varied in time, the atomic clock that's in the airplane and the atomic clock that was stationary on Earth, they varied in time. That doesn't need to happen because special relativity, because of special relativity. It could happen even if the special relativity was not true. It could happen even if time dilation is not true, and even if the speed of light is not constant to all frames of reference. So how is that? So if you place the atomic clock on an airplane, yeah, and the atomic clock is set, the frequency of the light coming from the producer of this radiation is set to 3 cycles per second, so the detector can detect these 3 cycles and then measure the amount of time that would pass depending on these 3 cycles. So when 3 cycles pass, the detector will measure 1 second have passed, and yeah, this line is the detector, and so on. If you place this whole atomic clock on the airplane, the detector will measure these 3 cycles and say that 1 second have passed, and measure 1 second passing, but more than 1 second will have passed, and that's because when these 3 cycles pass this point, like it normally would in the stationary detector, instead this time the detector would have moved to the front. Yeah, and when these 3 cycles pass this point, they pass this point in 1 second, because that's the frequency, 3 cycles per second. But the detector would have moved to this position, and not all the 3 cycles would have passed, even though 1 second have passed. But then when the 3 cycles finally passed the detector, more than 1 second would have passed. And that's why the detector would detect more time. The detector will detect that 1 second have passed when more time than 1 second have passed, and that means the detector will actually show less time passing than the time that the other detector on Earth that's stationary is showing, and which is what they said would happen because of special relativity, but it doesn't need special relativity because that's just what happens when the frequency when the same frequency of light is shining is going through a detector, and the detector is moving instead of stationary. So in an airplane, this frequency wasn't adjusted to the moving detector, so the time would vary, even if the speed of light is not constant for all frames of reference. So now we want to measure the actual the change in time that the detector would the amount of time that will vary in the detector, and compare that to special relativity's change in time, okay, or the time dilation's change in time. Okay, so to do that, we'll say that frequency is 3 cycles per second, and we will imagine that speed of light is 6 meters per second, and we'll see what happens, and we'll see the difference, the formula when these are the numbers, and then we will generalize the formula for any numbers, and then we can find the formula. And now imagine if the detector is or the airplane is moving at 1 over 6 of the speed of light, so it's moving in 1 meters per second. Yeah, and because the speed of light is 6 meters per second and 3 cycles pass per second, that means this point will reach this position in 1 second. That means because these are 3 cycles, so these 3 cycles pass this position in 1 second, so this point will reach this position in 1 second. And because the speed of light is 6 meters per second, that means this point will we'll move here in 1 second, so this distance is 6 meters, and that means, and 6 meters is 3 waves. That means each wave is 2 meters. That means the wavelength is 2 meters, and speed of light is equal to frequency times wavelength. So wavelength is 2 times 3. Okay. So now that we know this, how do we find the formula? Okay. So now, when these 3 cycles pass this position, the detector would have moved. So after how much distance will these 3 cycles when this point actually reach the detector? So to find that, we will say that the difference between the distances that this point moves and the detector moves must be 6 when this reaches this position, and that's because this point would have moved some distance and the detector would have moved some distance. So the difference between them originally is 6. So the difference between the distances is this 6 meters. That means that this point would have moved 6 meters more than the detector, which means it will reach the detector. Okay, so if the speed of this point is if the distance this point traveled is x meters, then the distance that the detector travels would be 1 over 6 of this distance, because the detector moves at 1 over 6 of the speed. So when this reaches the detector, the distance between the difference between the distances, which is x minus 1 over 6 of x times x, would equal to this distance, which is 6. Yeah, and that means that 5 over 6 x is equal to 6, and that means x is equal to 36 over 5. Now what's that in terms of these 3 numbers? Now first of all, this point will travel x distance. Detector will travel 1 over 6 because 1 over 6 of the distance, because it's 1 over 6 of the speed of light. So this 1 over 6 happens because of the speed of the detector, so it's caused by v, the speed of the airplane, and this 6 comes from the speed of light, because this is the distance when 3 cycles would have passed. Okay, so now this is the distance that this point needs to travel before the detector detects that all three cycles would have passed, and that means the point travels this distance, the detector will measure 1 second. So how do you know the actual amount of time that passed? Not because more than 1 second would have actually passed. So the actual amount of time that would have passed is, you can calculate it by saying that this distance over the amount of time that actually passed is equal to the speed of light, because this is light moving, and so the actual time that have passed would be what's over time divided by 6, so you get equals to 6 over 5, and you can see that the 6, which is the speed of light, cancelled with the 6 that was also the speed of light that came from here, speed of light. So you don't even need the speed of light, you need the ratio of the detector to the speed of light, which is 1 over 6. And if this is the actual time that that has passed, that means when the detector on Earth measures this time, then this detector will measure 1 second. And that means that the time measured by this detector I mean the time measured on Earth is equal to 6. So the time measured on Earth, or on the stationary detector, will equal to 6 over 5 times the time measured by the moving detector. So this is the time of the moving detector. And if we see where if you put the variables instead of the numbers, you'll get that this 6 over 5 is the same as t is equal to 1 for 1 minus x, where x is 1 over 6, which is the speed over the airplane over the speed of light, times t dash. And you can see that compared to the formula for time dilation, time on Earth is equal to root 1 over root 1 minus x squared times t dash, which is the formula for time dilation. The time measured on a stationary observer is this times the time measured for the moving observer, the time passing for the moving observer, and they are very similar. And yeah, okay, and I graphed these two formulas on Desmos, the graphing calculator, and you can see that they're very close together when x is large, and they only get far away as x approaches 1. And usually the speed of the airplane would be much slower than the speed of light, so the ratio between the, the, the airplane to the speed of light be 1 over a great number, so it will be somewhere in these places, and the results would be pretty much the same. And that's why you don't need time dilation to show these variations in the atomic clock the differences in time. It will happen even if light is moving at different speeds.